Hello everyone, today we have our lecture 8. Today's topic will continue our discussion on explanation of corrosion process on the basis of mixed potential theory and today we will consider two instances. I think it will be both lecture 8 as well as 9. We will consider situation two cathodic reaction and one anodic reaction. We have already covered a situation where cathodic reaction is 1 and anodic reaction is also 1. So, that means single cathodic and single anodic process reactions. Now, here we are considering two cathodic reactions and one anodic reaction, and the example being zinc dissolution and iron ferric ion reduction, and also if we put zinc in impure acid which is deaerated, that means there is no dissolved oxygen, but if we have a very small quantity ppm level content of Fe plus 3. So, then we can have these two cathodic reaction. So, these are the two cathodic reaction and this is one anodic. Now, we have to draw mixed potential theory. We have to draw those interactions of these reactions applying mixed potential theory. So, again the plot would be E versus log I, and here we are only concentrating activation polarization. So, our equation to indicate these three equations would be a general equation over voltage equal to the Tafel slope log I versus I 0. This is the general equation. If it is anodic, that time there would be positive and beta A. If it is cathodic, negative beta C log I, and here also if since it is anodic, in this case it would be cathodic reaction. So, since let us see where are those equilibrium potentials. Let us assume that the equilibrium potential of zinc, let us make it its equilibrium, its reversible potential. Let us say this is my reversible potential, which is if it is E equilibrium zinc, and since zinc is very active and if we consider this to be minus 0.76 volt, which is the standard reduction potential. So, even if the zinc ion content decreases, that means if we do not keep the concentration as 1, because when you are inserting zinc into the metal, the concentration of zinc in the beginning will not reach to 1. So, it will be less than that. So, this equilibrium potential would be further down if it is not unit concentration in that particular solution. So, anyhow, so this is if we assume that this is to be that particular situation, this is assumption, completely assumption, this is the potential. Now, this particular reaction if we consider, this is a very strong reduction potential, reduction reaction. So, we know E0 Fe3 plus Fe2 plus equal to 0.77 volt, which is very strong reduction potential, very high reduction potential, and E0 this is 0 volt. So, it means that the equilibrium, let us also consider the situation that pH, let us say 1, if we keep pH should be 1 or 3 or 2, any pH we consider in the acidic medium, considering that in the acidic medium this reaction would happen. So, this particular potential, let us say E hydrogen equilibrium. So, depending on pH, this equilibrium potential would vary, would be equal to minus 0.059 pH. So, now if I consider pH to be 1, then it should be 0.059 volt. Now, depending on the pH, this potential would vary, that equilibrium potential. Now, if this particular concentration, the Fe plus T concentration is very low, still if I assume that this potential, since there is a huge gap between 0 and 0.77, this is a huge gap between this reduction potential. So, it would lie this equilibrium potential Fe plus 3, Fe plus 2 equilibrium, it should lie above this point. Now, we have to consider their respective I0. Let us say this is the point of I0 of zinc on zinc. Let us say this is the I0 hydrogen on zinc, because if we have a solution deaerated HCl, let us say HCl. So, there we have those ions H plus as well as Fe3 plus, and now we have zinc block. Now, these two reactions, this reaction as well as these reactions, they must find some surface on which this reaction can happen. So, these are the surface over which this reaction would happen is basically the zinc surface. So, now that is what I0 hydrogen over zinc surface. Similarly, this ion is getting reduced to Fe plus 2, that reduction process would also happen on zinc surface. So, we can write this is the point, because these are the equilibrium potential and I0 always lies on equilibrium potential for the respective reactions. So, this point is I0 Fe plus 3 Fe plus 2 over zinc surface. Now, as per the mixed potential theory, they must reach to a point where this condition is met, where summation of IC equal to summation of IA. Now, if there is no Fe plus 3, so then it would have its own corrosion potential. That means, this is as per the single cathodic and anodic reactions, this is E cor, and I just put this particular situation zinc, because zinc is dissolved, and I cor is, so that means at this condition IC hydrogen on zinc equal to IA zinc equal to I cor zinc. Now, the other reaction is also following its own polarization. Let us say this is the polarization of the other reaction, which is Fe plus 3 plus electron equal to Fe plus 2. So, this is going like this, fine. Now, we have to maintain this particular criteria that suggests that whenever one polarization line, a particular polarization line, for example, here it is the cathodic polarization, the blue line is the cathodic polarization line for Fe plus 2 to Fe plus 3 to Fe plus 2. So, whenever it experiencing another cathodic polarization, those currents are to be added up. So, that means once it is coming to this much polarization. So, that means if the polarization level is this much, which is plus 3 to Fe plus 2, this is the polarization level for this reaction. So, here it is experiencing another cathodic reaction, which is hydrogen reduction. So, now as per this mixed potential criteria, we have to add up those currents, and then at this point we have to add total equal to I c of Fe plus 3, Fe plus 2 plus I c hydrogen. This is on zinc surface, this is on zinc surface. This is to be added up, and then we will take log. And so that means that log point will shift to the right, because the actual this total I c would be following a different line, which should be the current value should be at a particular potential. If I consider the particular potential, that current value should be little higher than that, because here this one and this one, these are added up and then taking log. So, it will come here. So, similarly, this one and this one, they are to be added up and then this point will come here. And now, you see that it will be parallel to that. So, then we have to draw this line. So, this is the plot of log of I c total, I c total. So, the I c, this I c contains current density, cathodic current density for this cathodic reaction as well as cathodic current density for this reaction. Now, if we extend this line, then I have to find out that point where this criteria is met, these two criteria is met. Now, if I consider there are 2 points, if I consider this point as well as this point, then we could see that at this point only I could see that I a zinc equal to I c hydrogen over zinc plus I c Fe plus 3 Fe plus 2 over zinc, and also it corresponds to a potential. So, this is E core mixed. So, this purple line actually, and cross section of that purple line and the black line for the zinc anodic line, that is the point we have to concentrate on, and that is the point the system would try to reach, and the corrosion rate of zinc would shift from this point to this point. Why? when we don't have this Fe plus 3 in this, that means it is a pure HCl, my corrosion rate was here. But once we added Fe plus 3 into this solution, then my corrosion rate has moved to this position. So, that means corrosion rate of zinc has increased and the criteria for the mixed potential theory is also met. And now, Ia zinc is nothing but the new corrosion rate of zinc when Fe plus 3 is there. Now, interesting part here, if we look at, if we see this particular mixed potential, that the new mixed potential when we have impurity in the form of Fe plus 3, I need to see the hydrogen evolution on zinc surface. Now, if you see the hydrogen evolution rate when there was no impurity, what is that hydrogen evolution rate? This particular point is the hydrogen evolution rate, which is nothing but, let us say this is, I term it as IC hydrogen on zinc surface when there was no Fe plus 3 ion in the solution. Now, once we have Fe plus 3, let us say this point is that I total. So, at that point, so corresponding to this point, okay, this is the new point, I would say hydrogen over zinc when there was Fe plus 3 ion. So, let me put it as prime. So, this is IC hydrogen zinc prime. Now, what happens once we have this Fe plus 3? When it was pure, the hydrogen evolution rate on the zinc surface was indicated by this particular rate. Now, once we have added Fe plus 3, my hydrogen evolution rate on zinc surface has reduced. Now, what could be the observation? The observation is unique. So, in the beginning when there was no Fe plus 3, we will see lot many bubbles of hydrogen on top of the zinc surface. But once we have Fe plus 3, since the rate of this rate is less than IC hydrogen on zinc surface when there was no impurity, when there was this is the case when there was impurity and this is the case when there was no impurity. So, now in this case no Fe plus 3, but once we have Fe plus 3, since the rate of hydrogen evolution is low on zinc surface, because that time the current density corresponding to hydrogen evolution at that new E core mixed is less. So, we would see that the hydrogen evolution on the surface is much less compared to this. So, here we have Fe plus 3. Interestingly, when we had no Fe plus 3, what was the polarization, the total polarization, the over voltage for the hydrogen evolution reaction? So, the total over voltage was this much, let us say this is nu 1, this was the over voltage when there was no Fe plus 3. Now, once we have added Fe plus 3, the over voltage has gone with reference to the equilibrium potential of hydrogen evolution to this. So, this is neta 2. So, we can say that the over voltage 1 is greater than over voltage 2. So, this is corresponding to with Fe plus 3 and this is corresponding to no Fe plus 3. Okay. So, now which one is larger? So, this one is definitely larger. So, that means once we have added Fe plus 3, the total polarization for the hydrogen evolution reaction on zinc surface has gone down. So, we can say that it has got depolarized. So, we can fairly say this is a kind of depolarization effect on zinc surface due to addition of Fe plus 3 and depolarization of what? Hydrogen evolution. So, actually I can say that depolarization effect on hydrogen evolution on zinc surface due to addition of Fe plus 3. So, we can also say that Fe plus 3 is acting as depolarizer. For the, so I can say that depolarization for the hydrogen evolution reaction. Now, interestingly, so if we consider that the hydrogen evolution rate over zinc surface is the observation for zinc corrosion, that means if we say that the more the hydrogen evolution on the zinc surface, more will be the corrosion of zinc, that may not be true. That means when we have a strong ion, strong reduction reaction, when we have a strong reduction, for example, this case or oxidant, a strong oxidant, because Fe plus 3 in this case is a strong oxidant which has a tendency to go to Fe plus 2. So, if we have a presence of strong oxidant, then there could be a situation that the zinc hydrogen evolution on zinc surface would be low, but the rate at which the zinc dissolution happens would be much faster than the rate at which when the observation was the hydrogen evolution on zinc surface was high. So, this is the reason for that situation, because when we have a lower polarization for the hydrogen evolution, I have much higher dissolution rate of zinc. So, on this particular issue, let us have some numerical problem. Okay. So, I have chalked down one numerical problem on this. That problem statement is like this. Let us say a situation where log I, and this is potential, and remember this potential with reference to standard hydrogen electrode. Okay. So, that time I can put some of the, so this same diagram let us put. This value is 10 to the power minus 11 ampere per centimeter square. This value is I0 Fe plus 3 Fe plus 2 over zinc surface is 10 to the power minus 9 ampere per centimeter square. When there was no Fe plus 3 ion, if there is no Fe plus 3 ion, so then this is the corrosion rate of zinc, which is I core equal to 10 to the power minus 8 ampere per centimeter square. This value, this I0 zinc over zinc surface equal to 10 to the power minus 11 again ampere per centimeter square, and the corrosion rate of zinc I core of zinc, I would say mixed, I just put mixed when that the mixed potential theory is getting applied. So, this value becomes 10 to the power minus 6 ampere per centimeter square. And few data that is given is beta is equal to 0.1 volt per decade of I, that current density. Why decade? Because beta can be considered as neta by log of I by I0. So, that is what I am taking per decade of, because this scale is in decade. So, now, so beta C, if we consider that time, it will be minus 0.1 volt per decade. I simply say decade of current density, I just omit this of I, rather I say we say volt per decade, and beta A equal to 0.1. There is a minus sign when we consider beta C, this is decade. So, this is the data that is given, and another data which is pH, because pH will decide what should be the E equilibrium hydrogen. So, not this point, this is the point which is E equilibrium hydrogen, that will be decided. pH, let us consider pH to be 3. Now, we have to find out what will be E equilibrium Fe plus 3 Fe plus 2, E equilibrium zinc, and IC Fe plus 3 Fe plus 2 at okay. So, no, this is not the case. So, the E mix when Fe plus 3 is present, E mix when Fe plus 3 is not present, as well as IC Fe plus 3 Fe plus 2 and IC H2 over zinc surface, both at E mix when Fe plus 3 is present. So, these are the parameters are to be found out. So, we will take this problem to our next lecture. Let us stop here. Thank you.